Hello, my name is Chongyu and my team members are Han Ting and Tianyu. So today I'll be presenting to you on our Quago project, which is on the IEEE CIS fraud detection. So to begin, we notice that consumers has become more and more tech savvy and their behaviors has been reshaped over time. And we notice that there is an increase in e-commerce sales from 3.53 trillion in 2019 and is expected to grow up to 6.54 trillion in 2022. Okay, and we also notice that the growth rate of e-commerce fraud are nearly twice as fast as e-commerce sales. Because e-commerce sales has been increasing, it is quite obvious that the e-commerce fraud will also increase as well. So therefore, it's very important for both consumers and business to be protected by fraudulent transaction. Okay, so the aim of our project is to be able to accurately detect transaction fraud. Okay, and this is to be able to benefit not only individuals but also business as well to reduce their fraud loss and also to increase their revenue. Okay, and to fulfill these requirements, we need to create a model, to create models to accurately predict fraudulent transactions. Okay, so how are we going to do that? Okay, so firstly, we'll perform data exploration to be able to determine all the interesting patterns in our data. Then we'll be able to use data visualization to observe the data properly to see any interesting points as well. Then thirdly, we'll conduct feature engineering to prepare a much more useful data set for our model. Then fourthly, we'll perform data cleaning to clean up on our data to remove unnecessary information. Then fifth, we'll perform data preparation to be able to train our models on, and we'll also be able to build our models using the data sets made specially for it. So the final model that we're using at the end is a weighted average ensemble, which consists of CAT boost, light GBM, and also XG boost. Okay, so for data exploration, we do that because it helps in our feature engineering stage. And for categorical data, we find out the number of any rows and unique value count. Then for non-categorical data, we look at the statistics, meaning the mean, standard deviation, and the percentile, etc. We'll also look for multicollinearity between any columns with the any value on the same row. Okay, we detect this multicollinearity using VIF, which is called variable inflation factors. Okay, low VIF value indicates low multicollinearity. So as you can see from our data, VIF value from V1 to V11 is very high, which means that they are most likely correlated to each other. But however, when we compare the values from V1, V12, and V35, we can see that it's below the threshold of 5, which means that they are unrelated. Then for data visualization, we'll be using Python's matplotlib library and also Savon library to be able to generate all our graphs and charts. Okay, this is to be able to help us to determine all the outliers and the variables that require us to do undersampling or oversampling. Okay, then we'll do feature engineering. So we'll make use of our understanding of our data to be able to create more features that are potentially more useful to improve our prediction models. So this can also be in turn to reduce memory usage as well as you're reducing all the unnecessary information. So we can do that by concatenating rows or even combining useful informations together. Okay, so we use principal component analysis on V variable to replace original variables with new ones. This is to reduce the multicollinearity and cut down on memory usage as mentioned previously. Then for light GBM, we'll create new columns that counts unique value in the original column of the unique variable. Okay, simplify the mapping of multiple email domains to the same value in the new column. So for example, if a column has A, B, C, and D as the unique value in the column, we count the number of occurrence of each unique value in the column. So let's say there are 500 rows where this value is A in the new column. We set the value of each value that has the value of A in the original column to have a value of 500 in the new column. So for example, rows with value hotmail.co.uk and hotmail.com will have the same value of Microsoft in the new column. Okay, we'll also create a new column that notes down the suffice of the email domain. For example, cable1.net has a suffice of .net and hotmail.com has a suffice of .com. Okay, for XGBoost and CapBoost, no feature engineering is actually done. Okay, so for data cleaning, we'll fill up any values and remove redundant columns and outlier to reduce the memory usage. Okay, so columns that are not used will not be used for, are redundant will not be used to train the model. Then for light GBM, we'll remove unnecessary columns like transaction DT and date from both the test and training data set. And we also remove outliers in transaction amount from our training data set. Then for non-categorical columns, we change the any values to the mean of the column. Then for categorical ones, we'll change the any value to a string value of n in n. Okay, so for CapBoost, we fill the missing values in our training and test dataset with a very high negative value of -999. We also remove transaction DT column because it's not needed as well. For XGBoost, it's very simple. We just fill the NA values with our dummy value of -999. Hey, so for data preparation, we will encode the categorical data so that models can understand or reduce memory taken up by the dataset. This is to speed up the computation and free up memory needed for our computation. Okay, so this involves oversampling or undersampling our datasets to create a more useful and a balanced dataset. So for light GBM, we convert all the categorical columns into categorical data type and set any values in any categorical columns of the test set which is not present in the corresponding column in the train set as unknown. Then we apply undersampling on majority classes in our dataset and oversampling in the minority classes. Okay, so one example of the oversampling of our data is on cut4 column. As shown in the graph, we can observe that Discover has the lowest number of record but has the highest percentage of fraud transaction. Okay, so this means that we may need to oversample our Discover transaction. Then for XGBoost, we convert the value in the categorical columns into numerical value. This can be done using our label encoder class from sklearn. So if there are n classes in a column, this label encoder class will encode the label in a column with a value between 0 to n-1. Then for model building for XGBoost, XGBoost is actually an improvised version of the boosted tree algorithm which focuses on model performance and computational speed. So we adjust the max depth parameter of the model to prevent overfitting and adjust the subsample and co-sample by tree parameters. So the max depth parameter refers to the maximum depth of the tree to be built. We want to limit the maximum depth of the tree as complexity increases with increased depth, which is more likely to cause overfitting. The subsample parameter refers to the ratio of data to be sampled from the train set, and the co-sample by tree parameter refers to the ratio of columns sampled in each iteration. This makes the training more robust to noise by introducing some randomness. After experimenting with different values, we found that a model with 9, 0.9 and 0.8 for max depth, co-sample by tree and subsample respectively generates the best predictions. So increasing the max depth appears to increase the score up to a depth of 9, after which the score starts to get worse. This may be due to overfitting at a higher depth. Private and public score is calculated from the ROC AUC score method of the sklearn metrics library. Okay, and for light GBM, it's a gradient boosting framework that utilizes tree-based learning algorithm. So we adjust the numleaf and max depth parameter of the model to avoid overfitting and adjust the learning rate parameter to prevent overstepping. So after experimenting with different values, we found that a model with 2 to the power 8, -1, and 0.01 for max depth, num leaves, and learning rate respectively generates the best results for the prediction. Similar to the XGBoost model, increasing the number of leaves past 2 to the power of 9 appears to worsen the prediction, and this may be due to overfitting with a larger number of leaves. Then for model building for CatBoost, okay, so CatBoost is a gradient boosting library tool based on gradient boosted decision tree that supports sophisticated categorical features. And unlike XGBoost and LightGBM, it does not require fine-tuning of parameters, so this reduces the chance of overfitting. But similar to XGBoost and LightGBM, CatBoost builds a set of decision tree consecutively, and each successive tree is built to reduce a loss as compared to the previous tree. The algorithm will stop once overfitting has been detected. Okay, so the final model, our weighted average ensemble. As we have learned, a single model based on one dataset alone may be biased and which have high variability or other inaccuracies that affects its analytical finding. And by combining different models together, we reduce the effect of such limitation and attain even higher accuracy. So we concatenate the prediction made by the three models respectively into a table and assign different weights to each prediction. And we optimize the weight using the differential evolution and give us a final set of weight of 0.512, 0.484, and 0.004 for XGBoost, LightGBM, and CatBoost model respectively. So with our final evaluation of our model, we managed to attain such rankings for each different model. So the lower the percentage, the higher the ROC score, which means that it is more accurate. Okay, so all the scores can be observed from here, and our final results are 0.941426, which places us in the 3,151 position out of 6,000 plus position. Although it's not the best, but I think it has come up to a great accuracy, which I find it quite a good result for us. So for our challenge phase, we find that the computing resource we are utilizing have limited amount of resources, and also our training and test data set provide differing column names, and there's no reference to our date time provided, and there's tons of missing data, especially certain columns of identity dataset, and most of the columns has large amount of NA rows, which make us not be able to use the columns effectively. So in conclusion, we have gained deeper insights into the field of machine learning and also hands-on practice by applying different machine learning algorithms. We also gain experience in pre-processing our data for a special model. We look forward to even more growth, knowledge, and experience and learning in the future with machine learning. Thank you so much for your time.